I'm going to be using some colors today. You can use whatever you want. I'm going to use my set of, what do you call these things, highlighters. Use pencil, crayons, whatever, doesn't really matter. And for the most part, it's just a matter of helping us see things. So up to this point in time in Science 10, we've really been setting the stage for this chapter. Okay? This chapter is all about chemical reactions. What we've learned is we've learned so what we've learned so far is really what are atoms, how are they made, how do you name compounds, and now we're going to take that information and we're going to put it to how do we make these things work together in a reaction. Okay? So before we do though, I want to start with just looking at this overview one more time. It's a little bit different this time. But looking at the overview just so that we get a sense of where we are in the process. So this is these are chemical divisions. And now we're going to, instead of talking about all matter, we're going to start at the top where we're going to talk about compounds. Compounds are broadly divided into two categories. The first one we call ionic. Of course, the other one is covalent, or if you wish, molecular. Okay? On this side, we remember that ionics are either one of two things. They're either, if they're binary, they're either a metal and a nonmetal, or they are a metal and a polyatomic ion. I'm just going to say polyion. Okay, so that anything that's of that type, ionic. Okay. The other one, covalent, are always nonmetals and nonmetals. Oh, thank you, dear. It is recording now. Thank you. No, but no, you need to be on me with that. I keep forgetting. Okay? Now, it turns out that within, from the covalent side, there are two possibilities. Well, okay. On this side, anything that's ionic is considered inorganic. It means from non-living sources. So I'm going to thank you for that. This is from non-living. Okay? But there are also, as we talked about in the last chapter, there's also the organic side. So these are chemicals that are from a living source or were living. Okay? So far so good? The inorganics that we have studied are come in three flavors. These are acids, bases, and salts. So for example, an acid could be nitric acid, A base, for example, could be sodium hydroxide. And of course, it is the H that makes these things acids, and it's the OH that makes these things bases. And then salts are ionics that don't have either of those. So let's say magnesium sulfate, so MgSO4. So that's an example of a salt because there's neither hydrogens nor oxygen or hydroxides attached, but they dissolve in water and they all conduct electricity. Okay? On the organic side, we haven't talked about this much, but I'm going to kind of like clue you into this. This is something more for Chemistry 11, but we said that there was a couple of groups. There was things that are called hydrocarbons, and you guys have actually seen these, and you didn't know it. These are butanes. For example, butanes, anything that has C's and H's only. Hydrocarbons, I ran out of space, sorry about that. Hydrocarbons, C's and H's. For example, the other day we looked at this guy here. You looked at this guy. We said that's butane. Okay. The simplest one is methane. You guys have all heard of methane. Methane is just a carbon. Oh. One carbon surrounded by hydrogen, that's the simplest. Ethane, the next one up. And it goes up from there. It goes up to infinity, kind of thing. Tom?
Why is it that the simpler the substance is, the more powerful?
Not necessarily. It's not entirely true.
I didn't know that.
You're looking at the fact that methane and butane are both highly volatile. You light them and they burn. Yeah. Some are actually burn faster, and they're not simple like this. But that's a good observation. But keep that for Chemistry 11, okay? That's a good question for Chemistry 11, right? So those are hydrocarbons. The other group, broad group, are things called alcohols. Okay? Now an alcohol is just simply something that has an OH on it, but is not inorganic. For example, if I look at methane, and I want to make this into an alcohol, I just take that off and put an OH on it. Remember, this is on your sheet. This was the CH4O. This is methanol. Okay? If I took ethane and I wanted to make ethanol, now it's ethanol. So those are two very common, very much part of our experience, everyday experience in organic chemistry. There is, in fact, a whole list of other types of critters that will blow your mind. There's aldehydes, there's ketones, there's carboxylic acids, there's and these are all just the really simple organic chemicals. There's things like cholesterol. There's things like cholesterol. All sorts of stuff. And so that's why this last one, I'm just leaving almost blank. This is just all other things. But in all cases, they all have to have C's, H's, and something else. Okay? A chemical reaction is a process in which chemical bonds are broken and new ones are formed. Okay? Here's some everyday examples. Here is an example that most everybody hates. This is rust. It's something rust. So we normally, when we talk about a chemical reaction, reactants are the species that will combine, or those are your start materials. Then it goes through some sort of breaking of bonds and rearranging of bonds, and what you have coming out the backside we call products. So those are two terms that we're going to be using a lot in this chapter. In this situation, you all recognize iron. Okay? So iron is a reactant, and oxygen is a reactant. And what will happen is, in certain circumstances, those two will react, and they'll form this guy here. Product is pink. This is iron 3 oxide. That's the chemical name for it. But here's the thing. When you're talking about chemical reactions, there is something that's called the should I talk about this now, or do I talk about this later? No, we'll talk about it later. In this situation here, what your challenge is going to be is to figure out how these things go together. Now, iron normally exists as a single atom. Okay? Oxygen, you guys know already, these guys are diatomic. So in nature, they live like this. I'm going to outline that just so that you can see these guys better.
Is it satisfying drawing?
I love drawing, man. I'm in heaven when I can draw or color. Okay? I try to color inside the lines now. Okay? And so what happens is, the big question is, if this is the product, what does it look like? Well, there's 2 irons and 3 oxygens, and so most of you, because you've done those Lewis dot diagrams, you're probably thinking, I need to make this as symmetric as possible. Now, how am I going to do that? Okay, I'm going to spare you the mental anguish, and I'm going to show you what it looks like basically. Okay? It kind of looks like this. Make sure you leave space between them. And I'm going to spare you the Lewis dot, what would you call it? Lewis dot agony.
Is there a reason why you're moving those colors?
Nope. There is. They're tricky. Okay? Keeping in mind that oxygen can only form 2 bonds and iron forms 3 bonds, this is what you should guess. these are oxygens. Each one of them is forming 2 bonds. This guy's forming 2 bonds, this guy's forming 2 bonds, this guy's forming 2 bonds. Iron 3 means that there are 3 bonds. This guy's forming 3, this guy's forming 3. Okay? If I was to have a pocket full of iron and a pocket full of oxygen, and I was to mix them together, what ratios would be produced is going to be the challenge that you're going to have to deal with for this entire topic. Did you have a question, Ms. Han?
Yeah.
We'll talk about that in a minute. Okay?
Also, why aren't the irons just opposite each other? Instead of like twice?
Can you sit in here?
The iron can have 3 bonds.
Yes.
It's bonded twice to the oxygen.
Yep. Yep.
Why aren't the irons just bonded to each other?
Okay, no, the short version, the best way to answer that question is a hard one. And what that would mean is you'd actually have to sit down, and you know how we've learned how to do Lewis dot configurations? Remember that? Okay, if I had you to do that, if you'd probably take you several tries before you stumbled upon a situation where you could actually complete the diagram and make sure each atom had 8 electrons on the outside of it, and everybody was happy. It's not easy. It's not really straightforward. Okay, that's why I've said I'm going to spare you the little Lewis dot agony, because believe me, it would be Lewis dot agony. The one thing that you'd have to say before you start that conversation, though, is remember what the second step in drawing Lewis dot configurations is. You have to arrange the atoms in the most symmetrical way possible. So if you've got 3 oxygens and 2 irons, what is the most symmetric way possible? Okay, the most symmetric way possible would be you would have oxygens like this, and you'd have irons between them. Oh, thank you. That's the most symmetric way possible. Okay? Now, the reason why it's like this is because their bonds actually form differently. This is more representative of what the molecule actually looks like, but if you'll notice, it's in the same order. Yeah. Yeah. If you want to do the Lewis dot configuration drawing, go ahead, but I'm not going to do it. You're on your own there, girl. Gee whiz. Okay? Now, we're going to talk about why it is that this is 4, this is 3, and this is 2 in a minute. But what I wanted to show you is this everyday example is a form of slow oxidation. The iron becomes oxidized. Yeah, this is an example of slow oxidation. The iron here becomes oxidized. It becomes joined to oxygen. Okay. This is slow oxidation. This is rapid oxidation here. So burning gasoline in a car. Now this is a simplified version. This is not, it turns out that this thing here is called octane. Notice that it is a hydrocarbon. It contains only carbon and hydrogen. This, I think gasoline is about 80-something% octane. It does have other things in it, but it's largely octane. So I just say, let's call it octane. And octane has 8 carbons and 18 hydrogens. So it's a long chain with 8 carbons in it, and hydrogen. And when it burns in the presence of oxygen, just like iron does. So our number 1 and number 2 reactants. And our products in this case are going to be carbon dioxide and water. Okay? And energy. Okay? Now, I don't know if I can actually do this. Oh, I better have something else. Come on, come on, come on. Let's see. I'm going to try. That's what, again, I don't know if I can. I should probably have something under this, don't you think?
Yeah, there was like drops on the base.
Okay, now I see a bright spot everywhere I look. This is not good. Now, what you should know is this is a metal, and Tom, you're quite right. This is magnesium. Magnesium, remember, is a metal. Whoa! Wait a minute. I once set off a fire alarm. It was not fun. Okay, now. Yeah, you see a line?
Yeah, it's like
Okay. This is magnesium. I burned it. What's that? What is that ash? What's left over? What is the product of this chemical reaction? Anybody want to guess? Well, it was also, you were quite right. It was the same chemical that you saw going into the air. Very good. What was it? Well, the smoke and the ash are actually the same thing. Anybody want to guess what it is? Okay, let me try to guide you in this. Let me try to guide you in this. The reactants were magnesium and oxygen. What was the product? There's something there. What was it? Or what is it? What must it be? Tom.
Is it
Magnesium oxide. Very good. That's excellent. This is one of those very few chemical reactions that is a combustion. This is called a combustion reaction, as this is called a combustion reaction. This is a combustion reaction, but at the same time, it is also a synthesis reaction, because I take two simple things and make something complex. Good job. So this is both a combustion and a synthesis reaction. It's both a combustion reaction and a synthesis reaction. We're going to learn about the different classifications of reactions in a bit.
Why did the fire go so bright and not just like normal orange?
It's just a property of magnesium. Magnesium, you guys, fireworks and stuff like that, you know that the brightness from them is from that metal. They use other metals too. Don't get me wrong. They use strontium. They use copper and well, mostly those are compounds of those metals. But magnesium itself burns very bright, and that's what gives it it burns actually very hot too. Okay. So if you, for example, if you mix, say, strontium nitrate, okay, SrNO3 2, and you mix magnesium together, and you light them on fire, what you'll see is you'll see bright, like flash, sparkly red. So if you think back to times that you've watched fireworks, and you have those things going off, those red strontium nitrate and magnesium. Probably magnesium nitrate too, come to think of it, because it's very reactive. Okay. Another one is this guy here. Hydrogen and oxygen will burn and it will it will also make water and energy. It'll make water and energy, and we can do that. If you, we can do this in class actually. If you take, say, magnesium that we just had, and you put it in hydrochloric acid, it'll produce hydrogen gas. And you can collect the bubbles of the hydrogen gas, and if you light it on fire, you'll get and you'll see water formed on the inside of whatever glassware you use. It's not as exciting as it really sounds, but it's better than kicking head with a frozen boot. Here's the rub though. And what does this look like? Well, let's use oxygen. No, let's use hydrogen is this. Hydrogen is diatomic always. And oxygen is diatomic always. And we know that water looks like this. Where you have like that. There you have water. Now there's a problem here. The first thing, the first question you have to ask yourself is, can you have this? Is this possible? Is this actually possible? I'll give you a hint.
Yes.
The law of conservation of matter says that you cannot create or destroy matter. Have I broken the law of conservation of matter here? I have. Why have I broken that law?
There's two oxygens, because they're a duo, and then in the H2O there's only one.
Yeah, so on this side I've got two oxygens, and on this side I've got one oxygen. So I just broke the law of conservation of matter, which means that this as it is impossible. How do I fix that?
And two more hydrogens.
Okay, am I there?
No, you need to draw the one.
Am I there? Calvin says we're here. Calvin is right. Okay? Look at this. Check this out. Two diatomic hydrogens plus one diatomic hydrogen is equal to 2 waters. What's the point of this? These are like recipes. Just like if you want to make brownies, there's, I'm guessing here, but there's probably eggs involved and cocoa and maybe some butter and maybe some milk and maybe some flour. And when you look at your recipe book, they don't say just mix some of this, some of this, some of this, and some of this. They say no. You take half a cup of butter, half a cup of milk, cup of cocoa powder, 2 cups, you blend it, put it in the oven, and happy days. So there's a specific ratio. So if I want to double my batch of brownies, I double everything. If I want a half a batch, I half everything. So what I'm trying to press on you today is when you look at these things here, I don't want you to look at it as if it's a bunch of chicken scratch. It actually has real meaning to it. Okay? Are we okay with this idea? Now, it may be that at some point you're going to be reduced to drawing pictures. That's okay. Because frankly, if you cannot develop a picture of how science works, you're going to be in a world of hurt for the next 3 years. 2.5 years. More than that if you plan to go to university. So you need to develop these pictures in your mind, okay? Another picture. Here's what we just did, in fact. Law of conservation of mass. Oh, go back. Take that page back. We are not finished with it. I want you to check something out here. Okay. If I cannot destroy matter, then I cannot destroy mass. I want you to look at this. If you look at your periodic table, and you look at the atomic masses of these particular critters, what you'll see is that every hydrogen is worth 1 atomic mass unit. We're going to average them, okay? So the atomic mass of hydrogen is 1. That's 1 there. That's 1 there. That's 1 there. That's 1 there. Are we okay with that? The atomic mass of oxygen is what? 16 for 1, right? So that means for diatomic oxygen, this is 16 and this is 16, right? Are we okay so far? That means if I was to take this and I was to put it on an atomic mass unit scale, all the reactants put on an atomic mass unit scale, how much would this weigh? Totally. Very good. This would weigh 36 atomic mass units. Okay? Now, how much does this weigh? 36. Now, let's pretend that instead of atomic mass units,
Wait, what is it?
36 AMU, atomic mass units. Okay? Now, let's say we don't like atomic mass units. Let's change the unit to grams, because we know what a gram is. We can weigh it on the scales in the back. So that would mean if I translated this totally, this would be 1 gram. This would be 1 gram, 1 gram, 1 gram, 16 grams like that. And so instead of 36 atomic mass units, this would be 36 grams. This, by extension, no big surprise, would also, or should also, equal 36 grams, right? Notice that no mass has been changed. The products and the reactants, the only thing that has happened is that bonds have been broken and bonds reform. There's been a rearrangement of atoms within to make new molecules. That's all that ever happens in chemical reactions. So when you saw, and this is why Tom nailed this sucker, is that when you saw that magnesium burning, he could say magnesium oxide. Because what you guys saw, and you didn't know it, was that the oxygen in the air, the bonds in the oxygen in the air were being broken in that incredible heat. And the magnesium bonds were being broken, and they were reforming to form magnesium oxide. And between the smoke and the ash, the mass of the smoke, the mass of the ash will equal the mass of that strip of magnesium that we started with. Okay? So here we are. This is exactly what happened. I'm not going to go through this. This is what we've just demonstrated. Since you cannot create or destroy mass, you must have the same amount of reactant atoms and product atoms. That's what we saw. That means you must have the same number of atoms on both sides of the arrow, of the yield arrow. Okay? Here's what we did, in fact. We took magnesium, took oxygen. Magnesium is a solid, oxygen is a gas, both in the air, and we produced magnesium oxide. Now, what you saw as smoke going up as magnesium oxide, that's actually a solid. It's not, it's lighter because it's being buoyed up by the incredible heat. But it's still a solid. They're tiny, tiny particles. So when you see smoke coming from a car, what you're not seeing is a gas. You are seeing particles, solid particles in the air. Okay? Nothing exciting there. This, to answer Miss Han. Han, or Han, Han. I'll get it yet. Okay, so there is a bit of notation when we talk about when we're using equations. The G stands for gas, L for liquid, S for solid. So if we run back to here, we see here, this means that iron here is a solid. This is a gas. Oh, this should be liquid here. This is a gas in the air, and you produce iron 3 oxide, or rust, which is a solid. Here we have octane in the liquid form, plus oxygen as a gas form, will produce carbon dioxide gas, gaseous or gaseous water, and energy. So that's what that's all about. Okay? The other one that is maybe a little bit outside of your you guys all take Spanish, yeah? No? Okay. You guys that take Spanish, you know that water is agua, right? Okay? Now, the word agua actually comes from a Latin word, aqua. So the word aquarium, when we talk about colors, aquamarine, that aqua part is all from the Latin word aqua, which means water. Okay? So if you see AQ, the word that stands for is aqueous. And all that means is that it's dissolved in water. So if I did this, if I said NaCl, aqueous, what that means is that I've taken salt, like table salt, I put it in water and mixed it up. And it's dissolved. It's completely dissolved. Okay? That's all it means.
Why is it saying
AQ. This here? Sorry, that's AQ. All right? I think you guys already get this because you've learned how to write symbols. Is that when you're talking about these different, this two here means that whatever is behind it, I've got that number of those molecules. So that this two means I've got 2 entire water molecules. If it's inside, if it's a subscript, what that means is that I've got 2 of whatever's ahead of it. And if there is no number here, that implies that that number is a 1. Okay? Whenever you see plus, you can think of it as combined, but that is not really true. It really means just and. Okay, now you can pretend that, but you can only say that if you're talking about the reactant. And the arrow is just an equal sign. Okay, that's all it means. Okay, so now we want to talk about, okay, what are we doing? Well, we want to learn how to write chemical reactions, to balance chemical reactions. So, I need some help. Mr. Houston and Ms. Baker, please. Oh, can I grab one more? Top. Okay. Okay. Before we launch headlong into balancing equations, the first assignment here refers back to the exercise we just did when we looked at the water, the mass of the water. Thank you, Cole. We looked at the mass of water. Now here's the idea on this worksheet, is that here's the arrow. So the total mass on this side has to equal the total mass on this side. And I think you get that from our example, right? We're okay with that? Are we okay with that? Mass of the reactants has to equal the mass of the products. So how do you solve for the missing mass? What will be your strategy? You have to figure out zinc chloride. How are you going to do that? Simple math, but what is your strategy? What are you going to do?
You're going to add the two masses together and then take 2 away from that side.
Okay, so let's do this first one together. So I've got 65.4 grams of zinc plus 72.9 grams of hydrochloric acid. So I end up over here with 138.3 grams of reactants, right? So that means how much zinc chloride I'm going to make if I only get 2 grams of hydrogen out of the deal.
36.3.
Excellent. Did you see that? So because whatever I have here, total here, has to be the same total here. So this has got to turn out to be 138.3 grams. Okay? So that means that this number minus this number is this. So thank you, Nathan. This is 136.3. Okay, so this is a simple 5-minute whip out your trusty calculator and through. Okay? Just be careful when you do this that I would suggest just drawing lines where this thing is. Just to help you in the process, okay? Okay. Now, I have written down the rules for how you go about solving a balancing equation. So what I'm going to do is I'm going to take this off screen because you have it, right? So you have this beside you on one side, and then you have this in front of you on the other side. So here are the rules. Number 1, write the symbols and formulas to represent reactants and products. Well, thankfully, they've done that for us. Okay? They've done that for us. And then the second rule is you generally start with the first atom on the left, which is going to be copper. Okay? You put coefficients. Now, coefficients are the big numbers up front. So these blanks represent the coefficients. Okay? These numbers you can change. The numbers here, these subscripts, you cannot touch. Because if you touch them, you have changed the chemical. It is no longer what you started with. So those are sacrosanct. Hands off. But you can change the coefficients. A hint, I'm going to give you 3 hints. Number 1 hint, leave diatomics to the end. If you have lone atoms or diatomics, you leave those to the end. If you have polyatomic ions that exist as polyatomic ions on both sides only, you can treat those like they're individual atoms. So you balance phosphates with phosphates. You don't have to break it up to P's and O's. Okay? We'll do some and you'll see what I mean. Okay? And then, at the end, you have to go through. If I say Etch-a-Sketch, do you guys know what I'm talking about?
Yeah.
The little dials, and you trace stuff over.
Yeah.
And then when you want to do a new picture, you have to turn the thing over and go like that to erase everything. Okay, so when you do your balance equations, so this is what I want you to do. Clear your head, and then count the atoms. Okay, here we go. Okay, moral of the story here. Watch this. Watch me do this one. First thing I notice when I look at this is I see that copper and silver are by themselves, so I'm going to leave the metals alone. I'm going to balance them last. The second thing that I notice is that I have nitrates existing as nitrates on both sides. On this side, I have 2 nitrates. This 2 tells me I've got 2 nitrates. On this side, I have 1 nitrate. Just hang a sec, don't get excited. How do I balance this? By putting a 2 here. This means that I have 2 of these and I have 2 nitrates. So now, this is what I do. You can do this if you like, you don't have to. What I do is I put a line or a dot above each one so that I know that I've already dealt with it. Where's my pencil? I just had the stupid thing. It was a good pencil while it lasted. Okay, I'm going to have to do it. Okay, so this is what I do. So I look at this and I say, nitrates are balanced. I look at this now. Because I put a 2 here, this also meant that I have 2 silvers. I have 2 silvers here. I have 1 silver here. So I'm going to put a 2 right there. It looks like I have 2 and 2, so these are balanced. See how the dot notation says, okay, you've taken care of those. Then I go and I say, what have I got left? I've got coppers. I have 1 copper here and 1 copper here. These are balanced. I have the same number on each side. Okay? Now at this point, I'm saying, oh, what a fine young chemist am I. No, you go, here we go again. 1 copper, 1 copper, 2 silver, 2 silver, 2 nitrates, 2 nitrates. Oh, what a fine young chemist am I. That's it. Okay? Let's go to the next one. You have aluminum plus sulfuric acid, or if you wish, hydrogen sulfate, aluminum sulfate, and diatomic hydrogen. This is similar to this one here in that I have aluminums living as atoms here and I have diatomics here. So my rule, if I have those guys, leave them to the end. Then, now what do? Well, I go to whatever's next. What do I have? I'm left with sulfates. Notice that I have 1 sulfate on this side and I have 3 sulfates on this side. So how am I going to balance this? Dear?
You add, like you put a 3 H2,
Right there, right? Perfect. So I'm going to put a 3 there, because that tells me now I've got 3 sulfates on this side, and I've got 3 sulfates on this side, so these are balanced. Okay, now I look at this and say, okay, what do I have next? Well, because I put a 3 here, that means that now I have got 3, watch this, 3 times 2 is 6 hydrogens here. I have 2 here. What am I going to do? Put a 3 here. 3 times 2 is 6. So I have 6 here and I have 6 here. Looks like those are done. What's left? The aluminums. I have 1 aluminum here. Oh, jeez. 1 aluminum, 6 hydrogen, 6 hydrogen, 3 sulfates, 3 sulfates. Oh, what a fine young chemist am I. Okay, notice that these things are going up in degree of difficulty, but not quickly. Iron 3 hydroxide. How do I know it's iron 3? Because hydroxide has got a combined capacity of -1. I've only got 1 of those. That means that he's got to be iron 3 hydroxide. Iron 3 hydroxide plus sulfuric acid, iron 3 sulfate, and water. Okay? So what am I going to do? What do I have? I don't have any diatomics or single atoms to worry about. So, but I do have, I notice I have sulfates here and sulfates there. This is a good place to start. So I'm going to say, okay, 3 sulfates here. That means I'm going to do what with this bad boy? That's right, I'm going to put a 3 here. So 3 sulfates and 3 sulfates looks balanced. What do I have now? Well, I've got iron. I've got 2 irons here, and I've got 1 iron here. What am I going to do? I'm going to put a 2 here. Okay, now this is a rule. It's just not a rule. This is a hint. When you get into situations like this, where you have a water available, balance. Leave the hydrogens to the end, and leave the oxygens to the end. Don't try to balance them right away. What you want to do is you want to go after the oxygens as your second last step, because if you balance the oxygens, it's like magic. The hydrogens balance right along with them. Go figure. Watch this, just so that you're convinced that I'm not telling a lie here. Okay. If I go back here, how many oxygens do I have? How many oxygens do I have? I ignore the sulfates because the sulfates are balanced here. This is an important point. Because they're polyatomic ions, I dealt with them like they're single atoms. They are now out of the way. They are out of contention. I look at here, how many oxygens do I have? How many oxygens do I have? Forgetting these guys on this side, how many do I have? Careful. 6. Right? 2 times 3 is 6. I'm going to balance the oxygens. I'm going to put a 6 there. Check this out. How many hydrogens do I have over here? 2 times 3 is 6. 3 times 2 is 6. 6 and 6 is? How many do I have over here? 12. 6 times 2 is 12. Now, ain't that magic? That's better than burning magnesium. That's crazy. How did that? I don't know how it works. I have no idea how it works, but it does. So just pat yourself on the back and say, what if I didn't have it? That's it. Okay? We will pick this up. Okay. What should you be doing? You should be nailing every Chapter 8 assignment. You need to get that out of the way. This is job 1. Okay? If you get that out of the way, my advice is to do this side. That's my advice. Okay? Tomorrow, I am going to spend the first little while, just hang on a sec. I'm going to spend the first little while asking if you have any questions for Chapter 8. Because after that, as far as I'm concerned, you're primed, you're ready for the chapter test. Okay? Then we're going to continue on. Love you, go away. Please put your chairs up. Oh, there it is.
So,
Go ahead. Give it to me again.
I'm on the online English course,
Yes.
and I'm behind quite a bit.
Yeah.
Basically, I have to make a rough draft for an essay and an essay, which are both practically due. And with the science homework that we receive each day,
Mm-hmm.
it takes up a lot of my time.
Yeah.
I also have a decently limited time after school because when my tail wears off, there are days when I have a very hard time focusing and then I'm not really getting anything because I can't focus. According to my online schedule, which isn't set in stone, but like it's to help guide me so that I finish the course when I need to. And yeah, basically I'm in the chapter 3, but which I have to do an essay, quote production, and all that stuff. And then the schedule is already starting next September. I think the chapter number doesn't matter. And so like, I don't really know. Largely I'm telling you just bringing it to your attention right now. But
You got a lot going on. Yeah, lots of us. Yeah, I get it. The thing that there's an upside of taking an online course is, like as you mentioned, is that it's not written in stone. The issue that I don't want you to run into with Science 10 is because it's hard. There's only one way to describe Science 10. It's called hard, fast, and continuous. It just does. It won't let up. Is that if you don't stay current with Science 10, you will get behind very fast, and you'll get into a situation. I've seen it happen before. Kids blow up. They just totally blow up, and that's why when I say to you guys, I say, okay, I'm being lenient so far as late marks are concerned, but the reality is if you're not on top of it, and you start to fall behind, it's very difficult to catch up. It just is.
if it ever came to this, is there any way of working when summer starts? Is there any way of